Hi all. In this video we are going to learn the flip-flop excitation tables. Okay, what are the excitation tables of different flip-flop? So this excitation table is very much required for the design of sequential circuits. Okay. This excitation table can be obtained from the truth table of every flip-flops. Okay, actually this excitation table indicates the inputs required to be applied to the flip-flop to take it from the present state to the next state. Suppose if the present state of our flip-flop is 0. Okay, suppose the present state of our flip-flop is 0. Okay, so we want to change that 0 to 1. We want to change the output of the flip-flop from 0 to 1. Okay, so for that condition, what are the possible inputs we need to give at the input terminals of an flip-flop? Okay, so that can be obtained from the excitation tables. Okay, so this is the excitation table of an SR flop. This is the truth table and this is the excitation table of an SR flop. And by observing that truth table, you know very well, and in the excitation table, here it is Qn and here it is Qn plus 1. Qn is the present state. PS means the present state of the flip-flop. Qn plus 1 will be the next state. Next state means after applying the inputs, the present state changes to the next state. Okay, that is after applying the inputs and clock pulse, Qn plus 1 will be our actual output. Okay, and for changing the present state to the next state, what are the available inputs we can apply at the terminals of a flip-flop? Okay, this is the required input for this transition. Okay, and we can consider the first case, that is the present state of a flip-flop is 0 and we want to remain that at 0. Okay, that is the present state is 0 and the next state also should be 0. That is, we want to keep the output of the flip-flop at 0. Okay, for that condition, what are the possible inputs we can give for an SR flip-flop? Okay, and by observing this truth table, we know that for the first condition, that is, we want to remain, we need the output of the flip-flop at 0. Okay, that is 0 to 0. So we can choose the first condition when S equal to 0 and R equal to 0. Okay, when S equal to 0 and R equal to 0, we know that the output of the flip-flop will not change. That is, if the output is 0, it will remain it as 0. Okay, so we can take the first condition, and also we can take the second condition, that is 0 and 1. If S is 0 and R is 1, we know that the output of the flip-flop always will be 0. Whatever may be the previous output, the next output of the flip-flop will always be 0. Okay, so here also we know that the output of the flip-flop is 0. So we can take this condition also. So for the first condition, that is 0 0 condition, the two input possibilities are there, that is S equal to 0 and R equal to 0, S equal to 0 and R equal to 1. And we know that for these two conditions, S is always 0 but R can be 0 or 1. So here we are writing S as 0 but R can be 0 or 1. Okay, so we are denoting it as using X. X means don't care, that is X means it can be 0 or 1. Okay, it can be a 0 or 1. Okay, and for the next condition, that is 0 and 1. Okay, that is the present state is 0 and we want to change it to 1. Okay, so for that condition, what is the possible inputs here? By observing the truth table, we know that for this condition, when S equal to 1 and R equal to 0, our output will always be 1. Okay, whatever may be the previous output, the next output will always be 1. So here the output is changing from 0 to 1. For changing the output from 0 to 1, we need to apply this input 1, s equal to 1 and r equal to 0. Okay, no other combinations are there. So here we are writing s is 1 and r is 0. Okay, and for also the next condition, when qn is 1 and qn plus 1 is 0, we know that is the output, the next output of the flip-flop must be 0. Okay, for that condition we can take this condition, this inputs, that is when s equal to 0 and r is equal to 1, we know that the output of the flop is 0. Okay, whatever may be the previous output condition, always the output of the flop will be 0. Okay, no other possible combinations are there, so we can write it as, for changing the output from 1 to 0, we have to apply s equal to 0 and r equal to 1. Okay, and also for the next condition, we want to keep the output of the flip-flop at 1. Okay, that is, if the present state of the flip-flop is 1 and if it has to remain 1, what are the possible inputs we need to apply at the terminals s and r? Okay, for the conditions, we know that here the no change condition is, therefore we can take the first one, when s equal to 0 and r equal to 0, the output will always be qn, that is whatever be the previous condition, it will keep on that state. Okay, so we can change the first condition, that is here it is 1 1. Okay, and also for making the output 1, we know that we have to apply a 1 0. Okay, for s equal to 1 and r equal to 0, we know that the output will be 1. Here it is 1. Okay, so the output will always be 1 here for this condition. Okay, whatever may be the previous output of the next output of the flip-flop will be 1. Okay, so two conditions are there, that is 0 0 and 1 0. In that, we know that this can be 0 or 1 and is r is always 0. Okay, so here we can write it as s as x and r as 0. Okay, so this is the excitation table of SR flip-flop. Okay, you have to learn well this excitation table for constructing our sequential circuits, that is counters, etc. Okay, and next one, this is the excitation table of an JK flip-flop. This is just same as our SR flop, little bit changes are there. Okay, so for the first condition, for 0 0, okay, what may be the available possible inputs for a JK flip-flop? Okay, here the output is not changing, so we can take the first condition, that is j is equal to 0, k is equal to 0. Okay, and we can also take this condition, that is 0 1. Okay, 0 1, for j is equal to 0 and k is equal to 1, the output will always be 0. So these two conditions, two input possibilities are suitable for the first case, 0 0. So j is always 0, but k can be 0 or 1. So here we are writing it as j is 0 and k is x, which means k can be 0 or 1. Okay, and for the next condition, that is the output is changing from 0 to 1. Okay, for changing the output from 0 to 1, the first input combination is 1 0. When j is 1 and k is 0, we know that the output will always be 1. Okay, so we can take first one, and also this is the output is changing from 0 to 1. This is the toggle condition, that is we know that when j is 1 and k is 1, the output will toggle. Okay, so we can take this condition also. So for the second case, we can take the last two conditions, 1 0 1 1, that is j is always 1, but k is changing from 0 to 1. K can be 0 or 1, so we can write as j is 1, k is x. Okay, and for the next condition also, that is output is changing from 1 to 0. Here it is the toggle condition. Okay, for changing the output from 1 to 0, we can choose the second state, that is when j is 0 and k is 1, we know that the output always will be 0. So we can take this condition, and also this is the toggle condition, output is changing from 1 to 0. So we can take the last state also, that is when j is 1, k is 1, output will toggle. Okay, so we can take the second and the fourth condition, that is j can be 0 or 1 but k is always 1. Okay, so j can be 0 or 1 here, so here we are writing j as x and k as 1. Okay, and for the last condition, that is output is remaining at 1. Okay, so it is a no change condition, so we can take the first condition when j is 0, k is equal to 0, no change will be there. And also we can take the third condition, that is when j is 1, k is 0, we know that output will always be 1. Okay, here output is 1, so we can take this condition also. So first and third we can take. So in that case, when we are observing the truth table, j can be 0 or 1 but k is always 0. Okay, for the first and third condition, j can be 0 or 1, that is x but k is 0. Okay, so this is the excitation table of a JK flip flop. Okay, and next one is the excitation table of a D flip flop. Okay, for a D flip flop, the output for the first condition, that is the present state is 0, next state is 0. Okay, for the output to be 0, we know that we have to apply D as 0. Okay, so here the D is 0. Okay, and also for the second condition, qn is 0 and qn plus is 1. Okay, so that is output is changing from 0 to 1. Getting the output as 1, we know that we have to apply d as 1. So here the d is 1. Okay, and for the third condition, output is changing from 1 to 0. For obtaining the output as 0, we have to apply d as 0. Okay, and for the last condition, fourth condition, output is keep on remaining at 1. Okay, that is 1. For obtaining the output as 1, we have to apply a d as 1 here. So this is the excitation table of a D flip flop, and next one is the excitation of a table of a T flip flop. And we know that the truth table of a T flip flop will be when t is 0, the output will not change, it will keep on at a qn. When t is 1, output will toggle. Okay, and here the excitation table is like that. For the first case, that is present state is 0, next state is 0. For getting the output as 0, okay, for getting the output as 0, here we have to apply t as 0. Okay, and here that is the no change condition, so the t will be 0. Okay, so the next condition is 0 to 1, output is changing from 0 to 1, that is a toggle condition. For toggling the output, we have to apply t as 1. Okay, this is the case here, so t will be 1. And for the third case, output is changing from 1 to 0, here also it is a toggle condition, so we have to apply t as 1 here. And the last case, the present state is 1, then the next state is 1, that is output is remaining at 1. Okay, no change condition is there, so we have to apply t as 0 here. So this is the excitation table of a T flip flop. So we have to learn the 4 excitation table of 4 flip flops very much, that is it is required to design our sequential circuits and counters. Okay, thank you.